We continue to study Feynman rules to understand the definition of cross-section. And T matrix element again is expresses a four-dimensional space-time integral of Lagrangian density. And in classical formalism, it is if we integrate over the space, then it becomes a Lagrangian, and the Lagrangian integrate over time. And we consider the fact that transition rate is increasing as time goes on. In the classical case, it used to be T matrix element squared divided by time. But if we consider the quantum interaction, then what happens? It should be integrated over the space again. That we have introduced the propagation of the potential in the space. So like if I make use of Lagrangian density function to compute the probability, transition probability, then it is increasing again with respect to proportional to time and space because of the four-dimensional delta function factor, right? It was squared, and the one factor is pulled out and divided by the time and space. So transition probability per unit volume and unit time is proportional to this energy momentum constraint factor divided by V to the force, that is a normalization of four wave functions for two currents. The two currents were made of, for example, if we consider charged scalar particles interaction with the photon, two scalar particle comes in, they interact with photon, and they change their momentum. This is the structure of our amplitude, and this M, invariant amplitude, was computed by making use of the Feynman rule, minus I current and the minus I current and propagator of the interaction. And two initial states are well prepared, and we cannot change the initial state. And final state PC and PD are constructed by imposing the energy momentum conservation delta function. That is, what is the P1? P1 is the current at this point, and P2 is the current at this point, right? That was related to the momentum at each vertex, right? This P1 is the momentum transfer at this point. That was a PA. If I put the full momentum of this initial scalar particle to be PA, and then PA subtracted by PC was the momentum of this P1, and P2 was the momentum of this point, this initial momentum subtracted by finite momentum. That was P2. If I substitute these values, then P1 is a PA, P1 and 2 are flipped. PB minus PD is a P1, and PA minus PC is a P2. If I substitute these values into energy momentum delta function, then it gives PA plus PB minus PC plus minus PD. That means for momentum, PA plus PB equals PC plus PD. Okay? These are simultaneous equations, right? Sum of the energy of the initial particles are the same, is the same as the sum of the final state particles. Sum of x component of the initial momentum is the same as the sum of the x component of the final momentum, and so on. So four constraints, energy and momentum, must be conserved. And if I introduce a new number density that is proportional to the energy, the 2E over V, we redefine the number density to be 2E over the volume, then the flux of the colliding particles, here we can consider these two particles, A and B, collide and then produce a C and D. The flux of these two particles can be computed by absolute value of the difference of the velocities in the frame where we are standing. And if we measure the momentum of A to be PA, momentum to be B to be PB, then this is the frame where we are standing. There we find the energy, the density of particle A to be 2E over V, right? Our space is fixed, but the box, we have a box. We are standing here, and there is a box that is moving to us to the right, and the other box moving to the left, and A is in here and B is in there. Okay? Then with respect to our size of our box, this box and this box, the two boxes are contracted, and density of two particles are increased in comparison with the frame where the particle is at rest, right? So we use our language, not their language, but our language. We are standing here, and A is contained in this box, and B is contained in that box. Two contracted boxes are colliding together. Then flux can be computed in our frame like that, and we have proved that 4 over V squared square root PA dot PB squared minus MA squared minus MB squared. All right, so let us go ahead with defining the cross section. Cross section is just the area, and it is related to the interaction rate. What kind of interaction rate? Let's see. In the classical definition, let us consider a continuous medium that is passing through some cross-section sigma. And if there is a number density m inside this cylinder, and this medium is moving to this cross-section in a vertical direction, then we can define the current density to be number density times drifting velocity. Suppose this drifting velocity of all particles are the same. Okay? Then if I measure the time, there's a V delta t, then if I count the number of particles inside this cylinder and the number of particles that passes through this surface, that hits the surface, will be just number density times volume. Right? So number density times volume. Am I right? Number N equals number density times volume. And what is the volume? Cross section times V times delta t, right? This is the height of this cylinder and cross section of the cylinder product. Sigma times the height is the volume of the cylinder. So during time delta t, this capital N, number of particles inside this cylinder, will hit this area. So definition of cross section is capital N, number of particles inside, divided by NV. That is current density. Current density times delta T. Okay? If I increase the area, the space where this current is flowing, then number of hits to this wall is increasing proportional to the area, right? So cross-section means if the flow is continuous, flow is uniform and continuous, then cross-section is proportional to number of hits. And cross-section is the number of hits per unit time, right? And cross-section is inversely proportional to this current density. And that factor exactly cancels in the number of hits. Normalized by, so number of hits normalized by time and current density. Or you can rewrite number of hits is cross-section times current density times time. So just like what we have used for the probability density, number of hits, this can be number of hits, number of interaction. So number of interaction is proportional to time and volume. But here, number of interaction is proportional to time, right? And area and density of the particles that is coming into the surface. Okay, if I have a single particle, this rate current density decreases, the rate will decrease. Okay, so cross section is number of interaction per unit time per unit flux. Cross-section can be interpreted to be number of interaction per unit time per unit flux. Okay? So I summarized everything. Cross-section is number of interaction divided by per unit time per unit flux, unit incoming flux. So the flux is just a relative concept. Suppose this guy is at rest, that then means just a single flux times number density of this object, right? So what we compute in previous case, probability density, the interaction probability was P matrix element squared by interaction time per volume. But if we interpret this in terms of the quantum mechanical way that in which the potential is a fixed at point, then this per volume is inside, included in there. So it was a number of interaction per unit time. But because we have spatial delta function 2, so this rate was redefined by per unit time per unit volume, in which the potential is distributed in the space. Potential is what? This is actually potential, right? This without that potential, this interaction didn't happen. Right? And even though I have drawn this Feynman diagram, what we have done is we have integrated the interaction point all over the space. We do not know whether photon is propagating from this point to there. We do not know. We have some size of capital V that is a very huge volume in comparison with the space, we have some target in here, and our space is very big, but in this volume, this V means this volume. And inside there, the photon is propagating here and there, and two particles come in and they collide together somewhere inside this volume. Okay? So I have integrated over all the points inside this eraser. So this spatial integral means some interaction space. But we have magnified that part. What we really see is nothing but, we don't see the eraser. Eraser is very small. But what we see is that incoming two particles and outgoing two particles. That's it. This guy is hidden. And we interpret this in using this kind of theory. Okay. So, number of hits per unit time is actually, in our sense, a number of interaction per unit time. This delta T and capital T over there is the same per unit volume. That is, per unit volume inside the eraser, where the potential is distributed. This is per unit volume. Okay. So, cross-section can be computed by making use of this transition probability, that is T matrix element squared divided by TV. And in a shorthand, we have found the final result, that is 1 over V to the 4th power to pi to the 4th power, energy momentum conserving delta function times invariant matrix element, invariant amplitude squared. But we find that there is another factor that should be considered. This energy momentum delta function is a very simple requirement, and that cannot restrict everything in a single point. The problem is that energy momentum delta function gives a PA plus PB equals a PC plus PD. There are many solutions that satisfies a PA plus PB equals PC plus PD. So we have to sum all over the possibilities of having PC and PD that satisfy the energy momentum conservation. That is called number of final states. So I have to sum over the number of final states that preserve the energy and momentum. That is, by definition, because this is that constraint, from next page on, we will pull this factor out, energy momentum conservation factor out, and multiply to the final state to define it to be what? Phase space. So phase space is defined to be times if there are particles in the final state, n particles, then multiply this kind of factor. And actually there is a volume factor appears, but we will eventually find that the volume factor cancel exactly, so we will not make use of this factor. So if we define this to be phase space, and actually this is the number of final states multiplied by energy momentum conservation factor, then this sigma is written in a very simple form. This sigma is invariant matrix element. Invariant amplitude squared divided by flux times d phi. We will study later in the next page. That's it. 왜? 안 끝.